Hello, this is Leah Murphy with another programming in ARM assembly video. Um, this one is a cool one, actually working with the board, whereas before we were just doing things purely in the software, not actually interfacing with the board. We're going to be reading in values from switches and adding them up to another value. Excuse me, it is a little bit late. I'm getting this done at 2, while there's Tropical Storm Ada coming through. So I've been distracted by the storm and other things. But I'm here, and I'm doing it, and it's going well for me. So, the whole premise of this, right, is, we've got these 8 switches here. Let's input it. We can input a number. Forget the lights that are on. Input a number, then input a second number using these same switches to output them to the LEDs. For example, if the number is 1 in binary, so if the number is 1, that's going to be flipped, and that's 1. If the number is 8, that's going to be flipped, and that's 8. And then this would be 9. So the LEDs in this example here that I have pre-set up would be 9 as the result. So now, how can we do that? There's a couple clever ways that we can do that. And the first one is by let's just think about it in terms of the actual switches. So let me get myself a brush. Cool. So we have how many switches on this board? We have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I cannot draw with a mouse. It's difficult. Okay, so we want to read in 2 8-bit values, and we only have 10 available bits. But how can we do that? Well, the first one we can do is select these 8 bits as the actual number. So, number. So those 8 bits are the number. We can read those in fine. We have 2 more bits. What can we do with them in order to read 2 different values, as well as selecting user input in order to output the result? Because you can input numbers all day, but you won't get a result until you tell the computer to print the result, or to send the result to the LEDs. So what we can do is we'll select this bit right here as the, we have 2 numbers, number A and number B, right? And now we can easily add that up back into the result. Well, that says result. So this would be A. This would be the A or B selector. So if that value is 1, the value is going to be A. If the value is 0, if the value is 0, it's going to be number A. If the value is 1, it's going to be B, okay? And now what is this last one? Bit 10. And bit 10 is going to be the result bit, or the user input result, like the return bit, you could say. So let's just call it return. Anyways, that's the whole concept. We read in these 8 switches, the number, then we can flip this switch here, the 9th switch, right? And select, let's go to B. We save the result in A before we do this, and then we go to B. We input a new number, and then and we'll save it to B. And then when we're done, we can flip this switch, the 10th switch, and return the result. So let's do it. I do have one thing set up, which I'm going to quickly not set up, which would just be by doing this, and then, okay, sorry, I am back, and all loaded up. I just had to double check what I was doing, because I sort of got ahead of myself. Let's not do that anymore. Let's go step by step, alright? Okay, so, basically, in the DE1 SoC board, which is the board that I'm using here, DE1 SoC, there are different addresses that are saved in a particular spot in memory that link to the location of the user input switches and to the LEDs. And those are included within a file called address_map_arm, which we have right here. So you see, in this file, which we are including into our main program, there are all different address locations for anything. You have the switch base, key base, you have everything. You have anything you need. You have switches, you have, timer, audio, anything, basically. The address where those peripherals are located. So using that, we can basically read the value at that address and determine whether a switch is, do a little bit of math and determine whether a switch is flipped or not. So ignore this, I will get back to that. So I'm just going to load, before doing anything, load values of 0 into register R3 and R4, which are both the two results, number A and number B, that I mentioned over here. Those are going to be stored in R3 and R4 respectively. Skip this line for now, and that one too. Now I'm going to load into R0 and R1 the addresses of the switch, and then the addresses of the LEDs. And now on this board, all of the switches, even though there's 10 of them, are all located at one address. Because there's so many different possibilities of numbers at that address. Instead of having 10 addresses, you only have one address, and you just determine via the number at that address which switches to turn on and not. The same thing with the LED. Anyways, that's all the initialization over with. So now I have our sort of main loop. And now, so we're going to load the value of load the value of R0 into R2, which is basically getting the value of the switch. So, for example, if the first one is flip, the value of the switch into into R2 is going to be equal to 1. Similarly, if I flip the second switch as well, it's going to be equal to 3, because it is in binary. So now I have this little compare statement, which is basically comparing the value in R2 to this number. Now, if we go back here, we have 8 bits. So what if this is a 1? Well, then we're going to return, right? Well, if it's a 0, we aren't going to return. So basically what I'm doing is I'm comparing the number that we have inputted here. So, for example's sake, let's just say 3. We're comparing 3, this number, 3, which is stored in R2, to this big number right here, 10-bit number, right? Let's say, for example, this switch is flipped. That's going to be greater. If it's not flipped, it's going to be less than. So we're comparing that. We're branching if it's greater to this sort of, I said return, let's just say return, it's more simple, to return, which is basically going to return. But for now, let's just assume it's not flipped. Now we're going to compare the bit right before. Now going back here, we have this bit, the A and B selector bit, which if it's 0, meaning if it's less than this value, if R2 is less than this value, it's going to branch up to a subroutine that's going to add the value A. Rather, if it's greater than that value, which means that this switch is flipped, we're going to branch to the subroutine that adds B. So, that's simple enough. Now we just simply have to branch these subroutines to get the job done about the actual adding. So this is just going to, I don't know why I wrote that. It could be move. I just did that to prove a point, writing subtract R3, or R3 equals R2 minus 0, just to prove a point. Because when I input this value with no switches, with none of the selector switches enabled, this value is purely going to be the whole value. I don't need to manipulate it in any way. This value is what it is. So I can just store that in the result R3, right? On the other hand, if the AB selector switch is enabled, then I'm going to have an extra 9 bits worth of I'm going to have an extra 1 in the 9th bit. that doesn't have anything to do with the result. So in order to fix that, you just have to subtract that. So in the B, because B would be when it's enabled. When B is enabled, I'm subtracting that value from the switch, from the whole value. And so you'll see when I run it, it's going to be R4. That's just going to be left with these 8 bits. Simple math. After it adds that, it's going to branch back up, compare it again with a similar idea, to the 10th bit. If the 10th bit is flipped, it's just going to go to return, or go to the answer. It's going to add up the 2 values and store them in R3. And now it's going to store R3 into the address, into R1 basically, which was the address of the location of the LEDs, which is going to light up the LEDs of our answer. So let us check it. Okay, so to initialize it, let's just do 3 plus 1. Easy enough. Or actually, let's just do 1 plus 4. Cool, that will work. 1 plus 4. Try to find the best example. Anyways, so we're just gonna step through this. You can see R3 and R4 are initialized. I have this in binary, so you can easily see what's going on in the 8th least significant bits. Alright, so step through it. Uh-oh, I accidentally played it. Let's not do that. So I'm going to initialize those values to 0. This isn't doing anything for the sake. Now I'm loading the addresses of the LED and switches into R0 and R1. They're already there, so I don't need to do anything. Now here's the main loop, right? So I'm comparing, getting the value of the switch. So in this case, the value of the switch is just going to be 1. So you can see R2 is going to just go 1. Well, it was already 1 anyways. Compare that, and it is, this switch is not flipped, so I'm going to continue on. Now this switch is not flipped, so I'm going to continue on. And then basically move this value into the result R3. Branch back up, and now this time I'm going to input my number that I want to add, which in this case is going to be 4. Okay. And then I'm going to select the AB selector switch to the on position. So now when I go through the branches, I'm going to load basically this entire value from the switches into R2, compare it with the value right here, and then branch if it's greater to B, which is going to add B. So I'm going to go there to B. Cool, worked. Now I'm going to have to do that subtraction that I talked about in order to get the actual value from the value of the switches. Cool. I have number 4 into R4. So now I'm going to go back. And now, in order to return, I'm going to flip the return switch. Okay. Load that value, compare it, and since it is going to be greater than the condition I set, we're going to branch all the way down to the answer, add up the 2 numbers, put them in R3. You can see we have 5, and store them into LEDs, and we have returned 5. That is amazing. That is great. It seems to work. One other thing you could do, and this is the other part that I had, is simply read from memory. In this case, I have number C, and the only change you have to make to do that is just change this condition to C, and everything else should work. Basically loading a byte worth of 8 into the .data location, taking that address into R5 and loading the value from that address into R6. Doing the same math right here, basically just except moving that value into R4, and then so I can add R4 and R3 again to get that. So I'm not going to step through that again because it would be going through and flipping switches, but it should take less time, so I'm actually going to do it. Why not? It doesn't take that much time. Just have to recompile everything because I did edit that. I sure hope that this video ends up working out with my phone. Sort of figured out a way to do it. Don't have any video equipment. Got a lot of audio gear because I'm a musician, but video, not really my thing. Anyways, let's continue. Alright, so I'm going to do 8 plus 1, 9. That's easy enough. Cool. So, I'm just going to skip ahead. Stop at the key points. Okay, I just loaded the first result, 1, into there. Into R3. Perfect. Now, flip the AB selector switch. In this case, it's AC. Or what I'm calling the number C that I loaded into memory beforehand. I'll load that in into R2. Basically move that value 8 into R4. Perfect. Looks awesome. Branch back up, and now I'm going to return the result. So flip that switch, the result switch, 10th switch, compare it, branch if it's greater, and now I'm going to turn on the LEDs. So you should get 9. Well, first I got to add it. So I have 1001, which would be 9. So let's turn it on. You can see 1001. It's the correct answer. Well, that seems to be about everything for this. Excuse my late video for this one. Got bogged down with some stuff. I hope everyone is staying safe with this tropical storm Eta. Being from Chicago, I'm not much used to it. So that should be everything. If you have any questions, feel free to reach out. I'd be more than glad to help or answer. Yeah, I hope this video turned out well. Thank you very much.